Children, in the last class, we have gone through the first topic of the prerequisites to learn linear algebra. Today, we will go through the second topic, matrices. The second topic, as I said earlier, in the prerequisites, the first topic was various sets like R, R2, R3, Rn, Pn, and F also I dealt with yesterday's in yesterday's class. Today we shall go through the second topic, matrices. And matrices also, the term you have already come across in your earlier classes, but today I want to recall all that you have learnt in the topic matrices in your earlier classes, as we need it in the linear algebra topic in the later classes. So what is a matrix? The notion of a matrix, the concept of a matrix we can see like this. If A is a m by n matrix with m rows and n columns, and capital A is equal to a matrix consisting of element of the form Aij as shown here with order m by n, where Aij is the ith row and jth column element, which is a scalar. Scalar in the sense each element of the matrix is taken as scalar. That means every element of the matrix is a real number, as I said earlier in the earlier classes. Now m by n, here the m by n term, m by n denotes the order of the matrix A, where m is the number of rows and n is the number of columns. And now we can see that capital A is equal to A11, A12, A1j, so on, A1n in row. The elements in row in the first row are like A11, A12, A1j, so on, A1n. Here A11 means the first row, first column element. A12 means first row, second column element. A1j means first row, jth column element. A1n means first row, nth column element. So on, if I say AM1 in the last row first element, then AM1 means mth row, last row of the matrix A and first column. AM1 belongs to mth row, first column element. So in that way, in general, we can say that ith row, jth column element can be represented as Aij, and the matrix itself can be written as Aij m by n, where I takes values from 1 to m and j takes values from 1 to n. The columns of A are vectors in Rm and are denoted by A1 bar, A2 bar, so on, An bar. Instead of writing the matrix so elaborately, we are making it into a simpler form by taking each column as a column vector and denoting it as some A1 bar, A2 bar, so on, An bar. So the first column of the matrix A is denoted as the column vector like A1 bar, and the second column is denoted by the column vector A2 bar, and the last column of the matrix A is denoted as An bar, and that is equal to A1n, A2n, so on, Amn column matrix. Each is a column vector of order m1, m by 1, and here whatever we are taking A1 bar, A2 bar, so on, An bar, which are vectors but nothing but they are columns of matrix A, and each of these vector is of order m by 1 because there are m rows and single column in each of the vectors A1 bar, A2 bar, so on, An bar. And so now the matrix can be briefly denoted as capital A is equal to A in the matrix form A1 bar, A2 bar, so on, An bar. Here remember that A1 bar is the vector is a column vector with elements a11, a21, ai1, so on, am1, as we can see here. So that is the way of matrix we denote in the later classes. So types of matrices now. What are the types of matrices? Let us see. In a matrix capital M by n order, if M is equal to n, if the number of rows is equal to the number of columns, then that matrix is said to be a square matrix. And if n is equal to 1, only n is equal to 1, then that matrix is called a column matrix. And that means if the order of the matrix is m by 1, then that matrix is called as a column matrix. If m is equal to 1, then it is known as a row matrix. If m is equal to 1 means the order of the matrix will be 1 by n, and if the order of the matrix is 1 by n, then it is known as a row matrix. Then the next type of the matrix is the entries. All the principal diagonal elements, or we can say the main diagonal elements, if they are same, actually not same, we are just talking about what are the diagonal elements here, and those diagonal elements are a11, a22, so on, ann, and these are called diagonal entries of the matrix A. These are the elements of the main diagonal of square matrix A n by n. If the square matrix order is n by n, then we can simply say that is an, because the number of rows and the number of columns are equal in the matrix, in the square matrix. Instead of saying an by n, we can simply say it is an. And if in such a square matrix an, if all the entries are zeros except the main diagonal elements, then it is called a diagonal matrix. So if in a square matrix except the diagonal elements, all other elements are 0, then we can say that that matrix is a diagonal matrix. Even if a non-zero element, one non-zero element is present in the main diagonal, that can be said as a diagonal matrix. That is why I have taken even the zero matrix itself can also be treated as diagonal matrix. That means not even one non-zero element. Every element may also be 0 in main diagonal also. So, but the main condition is that non-main diagonal elements. That means the elements not present in main diagonal should definitely be zeros. Whether the diagonal elements may 0 or may not 0, that is not to be bothered. That may be 0 or non-zero. As I have shown some examples here. In the first example, I have taken all the non-zero elements in main diagonal and all 0 elements in the non-main diagonal. That means all other elements. In the example B, I have taken all the elements as zeros. Even then, we can say that it is a diagonal matrix because the non-main diagonal elements are zeros. And in C, the example C, we can see the first element is 0. Even then, as all other elements of except main diagonal are zeros, it can be treated as a diagonal matrix. Now, if in a diagonal matrix, all the main diagonal elements are same, then it is called a scalar matrix. So, in scalar matrix, the non-main diagonal elements are zeros and the main diagonal elements are equal. I have given you 3 examples. Herein, we can see that the zero matrix with all zeros, all elements are zeros, is also a scalar matrix. It can even be a diagonal matrix, and as the main diagonal elements are same, all zeros, it can be treated as a scalar matrix also. And I want to give you some note points to be remembered now. The first point to be noted down is, if AN is a diagonal, if the square matrix AN is a diagonal matrix, then the condition should be Aij is equal to 0 for I not equal to j. So if we are saying that AN is a diagonal matrix, if the square matrix AN is a diagonal matrix, then what should happen? Aij is equal to 0 for all I not equal to j. That means A12 should be 0, A3, 1 should be 0, like that. And second note point is that AN is a scalar matrix if Aij is equal to 0 for I not equal to j. Non-diagonal elements are zeros, and Aij is equal to k for I is equal to j. That means main diagonal elements are same, where that k is a real number. Now the last point to be noted, the last but one point to be noted down is that a square matrix, in particular a scalar matrix, is called a unit matrix if all the entries in the main diagonal are 1 and all other non-main diagonal or non-diagonal elements are 0. It is also called an identity matrix, and it is denoted by In. So if in a square matrix, or particularly in a scalar matrix, if the main diagonal elements are equal and they are equal to 1 and all other elements are zeros, then it is called a unit matrix or identity matrix of order n. So the note point here is that In can be represented as the matrix consisting of Aij n by n order, where Aij is equal to 1 for I is equal to j. If I is equal to j means the diagonal element, and it should be 1, and Aij is equal to 0 for I not equal to j. And the last point to be noted down is that a matrix in which all entries are 0 is known as a zero matrix, and it is denoted by O. And so far what we have come across the definitions: diagonal matrix, scalar matrix and unit matrix, they should be definitely a square matrix. All those are square matrices, but a zero matrix need not be a square matrix. It may be of any order. So here I have given you some zero matrices as examples. First one is 2 by 2 square matrix, and the second example is of order 2 by 3. Still it is called a zero matrix. And the third example is 3 rows and 2 columns. So it is of order 3 by 2. Still it is also a zero matrix. Now what can we say about equality of matrices? Two matrices A and B are said to be equal if A and B are of same order. There should be two conditions to be satisfied if we say that two matrices are equal. What are those two conditions? A and B should be of same order, same type. Same type of matrices are same ordered matrices. That means they should have same number of rows and same number of columns. That means rows may not be equal to number of columns. The number of rows may not be equal to the number of columns, but in both the matrices the number of rows should be same. At the same time, in both the matrices the number of columns should be same. And the second condition for equality of matrices is that the corresponding entries should be equal. The corresponding entries means the first element, the first row, first column element in the matrix A should be equal to the first row, first column element of B, and so on. The equality of matrices we can represent like this. If A is equal to Aij m by n and B is equal to Bij m by n, then A is equal to B if and only if Aij is equal to Bij for I comma j. Addition of matrices. Addition of matrices, how can we do that? If A and B are two matrices of same order, then their sum A plus B is also of same order and is defined as A plus B is equal to Aij plus Bij m by n order, where A is equal to Aij of m by n order and B is equal to Bij of m by n order. And now scalar multiple of a matrix. The scalar multiple of a matrix is obtained by multiplying each entry of a matrix A by a scalar k, and it is denoted by Ka. If A is equal to 2, 1, minus 3, 5, this we can take an as example. If A is given in such a way, then 2A means multiplying each element of A by 2, we can obtain the product, the scalar multiple of A, which is denoted by 2A, and it is equal to 2 into 2, 1 into 2, minus 3 into 2, 5 into 2, and that is equal to, that implies 2A is equal to 4, 2, minus 6, 10. Regarding the scalar multiplication of a matrix, we have two note points to be remembered. The first one is minus A is equal to minus 1 times A, and the minus 1 times A means the matrix A should be multiplied by the scalar minus 1. And the second point is A minus B is equal to A plus minus 1 into B. That means we have come across in the last few minutes how to add two matrices and how can we do scalar multiplication of a matrix, and combining those two we can get the matrix A minus B in the way like this: A plus minus 1 into B. That means minus 1 into B is scalar multiplication of matrix B by the scalar minus 1, and then adding the resultant matrix to A. That gives rise to A minus B. Now properties of addition and scalar multiplication of matrices. If A, B, C are three matrices of same order is the condition here, and K, T are any scalars, then the first point says that, the first property says that A plus B is equal to B plus A. That means addition of matrices is commutative. The addition of matrices satisfies the commutative property. And then second point is A plus B plus C is equal to A plus B plus C. That means the matrices satisfy the associative property with respect to addition, or we can say that the associativity with respect to addition is satisfied in the matrix for all matrices. And then third point is A plus O is equal to A is equal to O. O means 0 matrix, and here it is A plus O is equal to A is equal to O plus A means O is 0 matrix here, and that both ways we can get A. That means O acts as O or 0 matrix acts as the identity element with respect to addition for the matrices. And the fourth point is K times TA is equal to KT times A. That means K times the scalar multiple of A by T is equal to KT times the scalar multiple of the matrix A. And then the fifth property says that K times A plus B is equal to KA plus KB. And sixth property says that K plus T times A is equal to KA plus TA. Now let us see how the multiplication of matrices is defined. Two matrices A and B are said to be conformable for multiplication. That means we can be able to do multiplication for the given matrices A and B. That we say by the mathematical word as conformable for multiplication, or sometimes we say that A and B commute for multiplication, or just A and B commute. So these are the things we use for we used to say that A and B can be multiplied. So two matrices A and B are said to be conformable for multiplication if the number of columns in the first matrix is equal to the number of rows in the second matrix, and the product is denoted by AB. So if A is m by n order and B is n by p order, then we can see that the number of columns in A is equal to the number of rows in B. If such condition is satisfied, then A and B are said to be conformable matrices for multiplication, and the product is denoted by AB, and that will have the order m by p. So we can simplify it not by writing the whole matrix. We can write the matrix B by representing each column by a vector B1 bar. Then B is equal to capital B is equal to B1 bar, B2 bar, so on BP bar. That means B1 bar is a column vector consisting of the first column elements of the matrix B, and B2 bar denotes the column vector with whose elements are the elements of second column of the matrix B. So on BP bar is the last column vector BP bar is the vector consisting of last column elements of the matrix B. Now, after writing B in that way, AB will be equal to, the product AB will be equal to capital A times that matrix B written in column vector form. This how we can do this while doing problems, we can see in the later classes. So on the whole, the product AB is now equal to the matrix consisting of AB1 bar, AB2 bar, so on ABP bar. Properties of matrix multiplication. If these properties hold good only when all these products are conformable. All these products are can be formed, then only we can say talk about these properties. The first property says that A times BC is equal to AB times C. That means the associativity with respect to multiplication is satisfied by matrices. And the second property says that A times B plus C is equal to AB plus AC. And the third property says that A plus B times C is equal to AC plus BC. That means the second and third are known as distributive laws. Left distributive law and the right distributive law. That means the distributive laws hold good in the matrices, in the set of matrices. And fourth property is that Ka times B is equal to K times AB, and that is further equal to A times KB for any scalar K. And the last property that is included in matrix multiplication is that IMA is equal to A is equal to AIN, where capital A m by n is a matrix. So if A m by n is a matrix, then IM into unit matrix of order m by m when multiplied to A m by n gives you A m by n again, and A m by n into I n by n gives you again the matrix A m by n. Note the points to be noted down here after studying all these things are that first point, in general AB is not equal to BA. Usually the product AB is not equal to the product BA. They may be of different order, or even if they are of same order, the corresponding elements may not be same. That is how AB may not be equal to BA. In some cases, AB may be equal to BA. In some particular cases or in some special cases, sometimes AB may be equal to BA, but in general it is not an universally true thing. So AB, in generally we consider that AB is not equal to BA. AB is different from BA. Even if the second point says that even if AB is defined, BA may not be defined for some given matrices A and B. So if AB may be defined for two matrices, I can give you an example here. If capital A is 3 by 3 matrix and B is 3 by 2 matrix, then as the number of columns in A is equal to the number of rows in B, we can commute them, and the product AB will be of order 3 by 2. But BA is not possible because B is of order 3 by 2 and A is of order 3 by 3. And here the number of columns in B is not equal to the number of rows in A, and BA is not possible. So we can understand that even if AB is defined, BA may not be defined for given matrices A and B. And the third point says that cancellation laws do not hold for matrix multiplication. That is, if AB is equal to AC, then we cannot say that B is equal to C. That is, B not equal to C in general. What happens is, if AB is equal to C, then B may not be equal to C. Usually it happens that B is not different from C. And fourth property says that if AB is equal to O, then it is not necessary that A is equal to O or B is equal to O. And the zero matrix, we call it as, we denote it by the capital letter O. That is how I am saying that AB is equal to O means O, by O we should understand that it is a zero matrix. Even if the product of two matrices is a zero matrix, we can not say that one of them is a zero matrix or both are zero matrices, because we can have some examples of such things where A is not a zero matrix and B is not a zero matrix, but still we can show that AB, the product AB is equal to a zero matrix. Next, that term we should know is, the definition that we have to know at this point is the transpose of a matrix. The transpose of a matrix A is denoted by A power T or A dash, and it is obtained by writing columns of A as the rows when we write the columns of A as rows or the rows of A as columns, whatever we get, that matrix formed is called A transpose or transpose of matrix A, and it is denoted as A power T or A dash. So when we change the rows of a given matrix A into columns, the obtained matrix is called transpose of matrix A. And if A by M in A, if capital A is a matrix of order M by N, then its transpose matrix A power T is definitely will be of order N by M. If A is of order M by N, then its transpose matrix will be of order N by M. Here A is of order M by N, then A transpose is of order N by M. So properties of transpose of a matrix are the next thing we have to go through. And the first property says that A transpose whole transpose is equal to A. That means transpose of a matrix is again A. So the transpose of a matrix A is equal to A. And the second property says that A plus B whole transpose is equal to A transpose plus B transpose. That means if we get the transpose of sum of two matrices A and B, which is denoted by A plus B, and that is equal to the sum of transposes of matrices A and B separately, A transpose plus B transpose. And third property says that Ka whole transpose is equal to Ka transpose. That means the scalar k, if we multiply it to A, the matrix A, then we transpose it, we get the same answer as the transpose of matrix A multiplied by the scalar k. And fourth property says that AB, the product AB whole transpose is equal to B transpose A transpose. This is to be remembered. AB whole transpose is equal to B transpose A transpose, but it is not equal to A transpose B transpose. Next, inverse of a matrix. If A and C are two square matrices of same order n by n, if A and C are, I am taking two square matrices of order n such that they are such that AC is equal to I is equal to CA, where capital I is n by n or I is nth order unit matrix, then AC is equal to I is equal to CA, then the matrix C is called the inverse of matrix A, and A comma C are said to be invertible matrices. So if AC is equal to I is equal to CA, then we say that the matrices A and C are invertible matrices and C is called the inverse matrix of A. And the properties of inverse of a matrix are like this. The first property says that A inverse whole inverse is equal to A. A inverse whole inverse means the inverse of a matrix A is nothing but the matrix A itself. So if we inverse a matrix, if we find the inverse of a matrix two times successively, then we will get the given matrix A itself. Then the second property says that AB whole inverse is equal to B inverse A inverse. This is just like AB transpose is equal to B transpose A transpose. In the same manner, AB whole inverse is equal to B inverse A inverse. And the third property says that A transpose whole inverse is equal to A inverse whole transpose. That means the inverse of a transpose of a matrix A is equal to transpose of the inverse of a matrix A. So whether we find transpose first and then find inverse, they are, if we find the inverse first then transpose it, they are one and the same. There is no difference between finding transpose first or inverse first. Whatever be the order of finding them, they are one and the same. So these are the things we have studied, have gone through this class today. First thing, actually there are 7 prerequisites that you should know before going to the chapter linear algebra. And what are those prerequisites? First one is various sets like R, R2, R3, Rn, Pn. Such sets I have dealt with in the last class. Now we have gone through the second prerequisite for linear algebra, that is the topic matrices. And in the topic matrices, that is already you have learnt in previous class, intermediate or so. But here it is the recalling of the same things, but sometime in some places we have come across new things also. What are the new things here? The columns of a matrix A can be represented as column vectors like A1 bar, A2 bar, so on, AN bar. This is the new thing for you. Or the whole part, the whole other part is already that you have studied in your earlier classes, except this column vector representing a matrix columns as column vectors. And now just see only this thing once again. So in the matrix A, the first column elements are taken in a separate matrix, and that matrix is denoted by A1 bar, and this is called column vector. and this is, even though it is written in the form of a matrix, we call it as a column vector or simply vector. And so a1 bar is equal to a11, a21, ai1, so on am1. That means a1 bar is a column vector of order m by 1, and a2 bar is the second column elements of the matrix A, and the second column elements of the matrix A are taken in a separate matrix like this, and that is denoted by a vector, and that is a2 bar, and that a2 bar is a column vector of order 2 by 1. And in the last column I have taken it as an bar, and that last column elements of matrix A are taken in a matrix, and that matrix is denoted by an bar, which is a vector, and that vector is a column vector of order m by 1. Each of these vectors, column vectors, are of the order m by 1. And in the product also I have taken that notation and defined the product. Product means multiplication of two matrices. There also we have used that concept. If we want to multiply the matrix A to a matrix B, then we are writing the matrix B. Write B as columns. That is, B is equal to a matrix consisting of vectors like this: B1 bar, B2 bar, so on, BP bar. That means B is denoted by column vectors. Instead of writing all the column elements, we are taking each column as a column vector in B and writing like this. And then we can find AB very easily, and AB is equal to A times B1 bar, B2 bar, so on, BP bar, and that will be nothing but equal to A B1 bar, A B2 bar, A BP bar. All these things we will come across in the later classes while doing problems, and then you can understand the thing more easy way. Now I will close the class for today. So we have finished off the second prerequisite to learn the topic linear algebra. So go through the class once again and make it simple yourself, understand it very well, and take down the notes or prepare the notes yourself on your own. Okay, children. So with this I am closing the class today. You learn the things at home and go through the previous classes also. In the previous classes I have told you what is the importance of linear algebra, and what are the things we should learn to learn the topic linear algebra. All those things in the previous class I have gone through, and just take, this is the third class for you to learn linear algebra, and please go through the last classes and get the subject very well. Otherwise in the later classes you won't understand the topic linear algebra very well. These are the prerequisites to learn linear algebra, and go through them properly, understand them properly. Okay, 1 minute. Okay, children, with this I will close the class today. This is the second topic, prerequisites for linear algebra, we have gone through. Okay. Okay, children, thank you.